All right, hey everyone. It looks like the number of attendees has kind of leveled out in the last couple minutes. So we're going to go ahead and get started. So this presentation is probably going to be about 15 or 20 minutes long, not a particularly long presentation. We'll try to get to questions afterwards, and we'll answer as many pertinent questions as we can. So feel free to ask away. My name is Daniel Young. I'm an application engineer here at Markforged, and I'm here with Alex Crease, who will be answering some of the questions during the presentation and assisting afterwards. So thanks very much, and we'll just get right into it. So first, a quick agenda of what we'll be doing. For a lot of the new listeners out there, we'll be introducing Markforged and just kind of talking about what we're about as a company and what we do. Then we'll be discussing why multi-part fixtures are a good idea and where they're pertinent. Then we'll be talking about design guidelines for them, things you should consider when you're designing these fixtures, and aspects of Markforged technology that you can leverage. Last, we'll be going over some implementation examples. So we've actually designed a few of these fixtures as examples, and we'll kind of explain to you aspects where we've integrated the strategies we'll talk about earlier in the presentation, and how you can kind of leverage this in your own workflow. And last, we'll open up the floor to questions. So first, a little bit about Markforged. Markforged was founded 4 years ago out of MIT with the goal of removing the barriers between design and final products. So really what this means is enabling users to print strong parts and use those parts in real applications. We know that 3D printing has been around for a while, but that was the goal that we were trying to change. So since that, we've expanded to every continent except for Antarctica. We print all over the world, and people all over the world have started to leverage our parts to improve their manufacturing processes worldwide. We're especially big in the United States and Europe, and we're working on expanding to other areas as well. So what do we do? In short, we make the world's most advanced 3D printers. The reasons we do that are fourfold. First, we have high precision and repeatability across every aspect of our product, whether it be the build plate or the gantry or the actual stage that the build plate clips into. So a lot of aspects of our parts are made precisely, and that means that the parts will be made precisely as well. On our printers, we have advanced sensor suites to recognize how the parts are printing at any given point in time. And that, coupled with in-process inspection on our more expensive lines, means that you can actually inspect the dimensions of a part while you're printing it. So this print is a fully enclosed experience where you can look at your parts online and see how they're printing, what dimensions they're printing at, and whether or not you should continue printing them. And the last thing is it's built on a robust printing platform, whether it be our software Uyghur, which you'll see hear us mention several times in the coming presentation, or the actual printer itself, which has reinforced gantries, a super precise build plate, and an all-metal construction. That means that we're able to get that precision and repeatability that we mentioned earlier. So that's kind of where we are from a printer perspective, but that's really not all. We have a really wide range of material that we're able to print with, whether it be plastics, which most FFF printers print with. In our case, the reason our plastics are special is that they have chopped carbon fiber in them, which gives them better dimensional accuracy, stability, toughness, and overall strength, which allows them to go in a lot more abrasive and rough environments than you would see most other printed parts. Within those plastic parts, we can also lay continuous long-strand composite fiber. So in our case, we have fiberglass, which is kind of shown in this photo, but we also have carbon fiber, Kevlar, and high-strength, high-temperature fiberglass. So these materials allow you to leverage the plastic printing that you know with extra strength to make more stronger parts. So with composites, you're able to reach the strength of aluminum, which is really great. But recently, we've also launched a metal line of printers, which allows you to, instead of print like metal, to print an actual metal. And so we're leveraging a combination of a MIM process, which is well known, and FFF printing to print these really strong metal parts that will still be delivered on the same time scale, but at a much cheaper price than you would see any other metal printer. So that's kind of what we do from a materials perspective, and really what it all boils down to, again, is same-day strong parts. So our goal is to enable users to have parts to CAD a part, to print that part, and to have it come off the build plate in the same day or in a couple days if it's a giant part, and be usable in a manufacturing context. And so some of these same-day strong parts that are best suited for our printers are fixtures. So now we'll kind of get into why multi-part fixtures are useful. So first, we'll kind of go into a little bit of an analysis of current fixtures. So current fixtures are often kind of fall into two buckets. They're either really rudimentary, so there are a bunch of parts like this fixturing system on the right that has a bunch of interesting modular fixturing apparatuses, or they're really expensive and custom. So that means that they're either take a long time to set up or they take a long time to make. And so these are both things that are not really optimal from a complex fixturing perspective. And printing fixtures makes these complex geometries more accessible because you can utilize simple CAD techniques to get these really complex geometries that are then compensated for in these fixtures. And the last thing is that multi-part fixtures, as opposed to single-part fixtures, allow these complex designs to be easily swapped. So if you have multiple fixturing things required on the same machine, or you have multiple revs of the same design, you can really easily kind of work with that. So that's why modular fixtures are a really good idea. And overall, that's kind of what we work with. So the last thing is that you kind of need to make fixtures strong. People have tried to print fixtures for a long time. The problem is that most printing plastic materials are not robust enough to actually handle it. So you either take a long time machining a complex fixture that will work but costs a lot of money, or you print a really cheap one and you expect it to break after 1 or 2 times. The unique thing about our parts is that with this fiber reinforcement, as you can see with this continuous Kevlar cutaway on the right, we're able to get this really strong these really strong fixtures that are still plastic and readily printable. So these joined multi-part assemblies in particular are able to provide more planes of fiber strength. If you have one part, the fiber orientation is constrained by the build orientation. If you have multiple parts, you can print them in different orientations and leverage multiple planes of fiber strength. So that means that they're optimized to perform in the use case necessary, whether it be loaded in one plane or several planes or in every way. And so kind of now we'll get into the design guidelines of how you can leverage Markforged to utilize this actual strategy. So there's a few basic guidelines we want to talk about. So first, making a distinction between multi-part and single part. So this soft jaw on the right is a part that we bring to every trade show. It's a great single part sample part fixture that's a soft jaw. And so a lot of these soft jaws or robot arm end effectors or these other fixtures are really great single part fixtures. They're not complex enough and they're not loaded in enough ways to provide a need to be a multi-part fixture, but they're also still really good fixtures to print. So in this case, this is a fixture for a machine part, and it's super simple. It's a super simple geometry. You obviously print it with the backside down, and that complex geometry you can see on the top is just printed upwards, and it's a very easy part to print. The other interesting note is that most soft jaws in these type of fixtures are loaded in compression. And compression is a pretty easy load case to compensate for with our fiber. So with these multi-part assemblies, they work better for 2 different ranges of fixtures. One is more complex fixtures, and the other is higher load fixtures. So the reasons these work better is that, as we mentioned before, they can leverage the multiple planes of fiber strength. And also in a higher load scenario or in a load case where maybe it's not all on compression, a multi-part fixture can end up being stronger for the application you're working with. Cool. And so the real linchpin of multi-part fixtures is this clamping force that we kind of can achieve with bolting or any other clamping strategy that makes the z-axis strong. So as many of you know, the standard weakness with FFF printing is that the z-axis strength, because of the way the material is extruded, is inferior to the other 2 axes. And this holds true with our machines. The wonderful thing about our parts is because they have this fiber, you can use bolts that will clamp the part and prevent that z-axis from separating. So this example on the right is just a kind of an isolated example. We'll show more detailed examples as we get further in this presentation. But what you can see is this bolt is just simply being bolted through this fiber reinforced part, and because there's fiber in this part, it's able to distribute that clamping load over the entire part surface. So what that means is that even though you're only clamping this part, in this case 1, but normally a few areas, those few areas are still able to produce enough clamping force to prevent that part from separating, because you're clamping a fiber mesh that wants to stay stiff. So then if you're trying to separate, you can pull apart a small area, but in pulling that apart, you're trying to bend a fiber mesh that will not bend. So with that, most bolted clamp plates that we'll talk about will utilize the strength advantage, and a lot of the multi-part fixtures you'll see will involve a bolted clamp plate, in that they're bolting to some metal area and then have some other complex geometry that's coming out from that in the form of a post or in the form of another clamp plate. So this is kind of the key to understanding how we do what we do from a multi-part fixture perspective. So just a quick note on joinery basics and kind of what we will work with. Joinery generally has two components. It has a mechanical constraint and a fixing and adhesion. So generally, the better the mechanical constraint, the less robust the fixing adhesion needs to be, and vice versa. The more robust the fixing or adhesion, the less strength the mechanical bond has to be. So in this case, we have two examples on the right. The top one has a very strong mechanical constraint, which is a dovetail joint. So this has a lot of surface area, which equals generally a better, stronger joint, and it's physically constrained in more than two axes. So in this case, we just use a small pin to hold it in. And it's fair to note that that gray part is like a base plate that would be printed with that bottom edge down, and this dovetail was kind of similar to what you would see from a post, where the plane that is currently on the screen would be rotated and printed downward. So these parts are printed in two different orientations. So then if we look at the bottom part, we're looking at what we call a captured nut. So that upper recess has a nut inside it with a bolt screwed through. Since this part has a more robust fixing mechanism, a pin doesn't have any axial constraints, and a bolt does. We need a less strong joint, so this is a much more simple lap joint. And so this holds true across any joint where both more surface area equals a better joint, and more axes of constraint means that the actual fixing or adhesion method needs to be less strong. And the last thing is that, which we've kind of discussed when we're going through these examples on the right, is that the orientation of our joinery matters. So you really want to print to leverage the fiber strength. The reason I discussed that dovetail orientation is that we're leveraging that clamp plate advantage that we have with that bottom gray part, and then printing that dovetail face down means that you can put fiber in that whole dovetail. This particular cross section, it's important to note, has the pin going through it, but the pin, there's not going to be a pin in every layer of that. It's only going to be in a few layers. So normally the fiber would be able to go across that pin because there would not be a cavity there. So one more quick note about fibers. We're not going to discuss glues and joints too much here because they often work better with multi-part assemblies, or when it comes to prototyping or some other thing, or more permanent joints. We're going for more of the fixturing area. But we do have a glue that we do recommend. This is a commonly asked question, and the glue we recommend is Loctite 401. It's a cyanoacrylate, and it bonds really well with onyx. Generally, what we say is that the glue bond strength is equal to or greater than the plastic material strength. So basically, if you have two parts and they're printed well and dimensioned well, and you glue them together, it is roughly akin to printing one part. It will not have the same strength as the fiber reinforcement that we discussed, but it will have the same strength as the plastic. So that's a really important thing if you're trying to print really large fixtures. We don't have any of those right now, and we're not really going to discuss that in this webinar, but we're happy to answer some questions about that afterwards. So the last thing we're going to talk about in this webinar before opening it up to questions is a couple of examples of implementation. So we CAD'd up and designed a couple of fixturing examples that we'll discuss through that have a few of the strategies that we just discussed in the previous section. So the first one is strong bolted fixtures. So in this case, this is a bolted welding fixture for two steel tubes or pipes that are at an interesting orientation at a very acute angle. So normally work holding for this would be very difficult. You might use some sort of helping hands to approximately orient them, but they would not be exact, and it would be very difficult to do without machining a more complex collaring system. So this printed assembly is very simple, and it really allows you to get a lot of strength and ease from a fixture like this. So in this case, we have three components. The first one is that base, which is shown in the Uyghur screenshot on the top, and it's reinforced by fiberglass. So that base is bolted down, which gives us a lot of strength from that to that aluminum breadboard that it's bolted onto. And then we have two clamp plates on top of it. And so in this case, all of the bolts are removable. So you can really easily remove those bolts and get the two clamp plates off, or you can take the entire fixture off from that breadboard, which means that the part is really easily removed from the jig even after it's welded. So the last thing is that throughout this whole part, all three of these parts, we have fiberglass. And in the case of the clamp plates, what it's doing is, as we mentioned before, distributing that clamping load over the entire tube surface, which means that we're getting more surface area clamping on the tube, which means it's a better fixture. And since we're clamping with a lot of plastic instead of a few points of metal, which you might expect from another type of metallic fixture, a quick metallic fixture, we're preventing deformation across the part. So again, this is a really simple welding fixture which you could use 1 time or 100 times. But it's a really useful example. And one thing to note is that obviously if you tried to weld the onyx itself, it would melt. But generally what you would do in this strategy is just tack that joint a few times and then take it out and finish the weld in another place. And that way you would prevent the heat exposure, which onyx is not bad with, but definitely is not capable to withstand welding temperatures. So the second fixture we have is a CMM gauge, or basically a gauge that holds a cast and machine part, in this case, in a certain orientation so that a laser scanning system can take the dimensions of it. It has a couple different areas of joinery strategy that we'll discuss. So the first one is these pin joints. So the first thing you need to understand about CMM gauges, they need to be very accurate. They need to hold the part precisely, and they need to hold the part securely so that when it's scanned, it doesn't move at all, so they can get a very precise reading. So with pins, you're able to precisely locate these posts on that base plate. So again, this part has a base plate that's bolted down and then several posts that go upward. And as you can see from that call-out graphic and the little drawn pin, there's a couple pins inside that assembly there that are locating that post very precisely relative to the base plate. And what that allows us to do is both change the design of the post if we want, because then we just take it out and add a new post in and put it in on those pins, so it's removable. And it allows us to align it much more precisely than if we just use bolts. Because bolts are threaded, threads are not very precise from a radial perspective, whereas pins are. So these pins are kind of fixing it in an XY plane and making it very strong. So the last thing, the second example we'll discuss here is using captured nuts for easy strength. So the first nice part about using a captured nut is, as you can see from the call-out, the nut stays inside the part envelope. So when you have a part like this fixture here, that means you don't need to add an extra flange for the post to bolt down on. You can just leave a cavity inside that post and put the nut inside, and there's no extra printing required. The next thing that's more of a usability thing than anything else is, once you've set this capture nut in, there's no wrench required to tighten, which means you can just kind of screw it in as if you're bolting a little bolt or screw into a normal tacked hole. And so that gives you a nice little usability boost where you don't have to hold a nut in a weird place and add it, and makes it super fast to use. The last thing is that when we're using these nuts, we're reinforcing that cavity with fiber. So if you look at that Uyghur screenshot on the bottom of your screen, that's basically a laid down view of that same post that we're taking a photo of, and you can see those regions of fiber, of those regions of fiber reinforcement right near the nut cavity, particularly on the top right corner of that part. So to be clear, this part has both pins and bolts in it on both of these posts, where the pins are securing the part on the XY axis and the bolts are securing it along the Z axis. So using these multiple methods of fixturing allow us to create a really strong fixture that you can use repeatably and easily. And so this is kind of the conclusion of the examples of our webinar. And so I'd just like to thank you guys for attending and opening the floor up to questions now. All right, so how does laying fiber in the XY plane help with strengthening the Z direction? So that's a question we can go back to this slide here. It's an interesting question because it's pretty counterintuitive. So in the normal world, it does not. But what it does help is when you couple that with bolting a part through, because that bolt provides a clamp force. So basically, you're clamping this entire part, and since these XY layers have discrete fiber, that means that in order to basically tear this part apart, you have to bend around those bolts. So you could still theoretically separate it in the Z-axis, but what you would have to do is pull it apart and have it split along the layer line, and then those two layers would have to bend relative to each other, and that's where the XY strength then comes back in and helps with the Z. Because you have that fiber reinforcement in the XY axis, your parts are going to resist that bending, which means that you're going to see a lot of extra strength in the Z-axis you wouldn't see before. So we keep talking about precision. I was wondering if you're able to how precise it is. Precision on extrusion-based 3D printing depends on a lot of factors. But one of the key things that we discussed in our original slide is that's precise and repeatable. So generally we say precision is precise to somewhere in the 5 thou range with Onyx. Onyx is a very precise printing material. It's so dimensionally stable that once you have your printer dialed in, it will just print very well. So that's a decent accuracy. The even nicer thing about that is that Onyx is repeatable to about 2 thou. And the reason is that as long as you can print a unit test and verify dimension or see where it's off, you can adjust that dimension and have it print right. So if you go all over our website, we kind of have examples of unit testing and printing precise assemblies. And so there's examples of that all in our blog and in our resources page. Can you vary the density of the carbon fiber in the part? So yes and no. So for the Onyx, which is the chopped carbon fiber thermoplastic, that's set. You can't vary the amount of chopped fiber in that part. But with the amount of continuous strands, you have a ton of granularity about how much fiber you can put in a part. There's a bunch of extra video assets and assets on our website as well that kind of detail how you lay out fiber in our parts, because it's a little less intuitive than your typical CAD program. But once you learn, it's pretty easy to do. So the answer is yes, you can put as little as 1 loop of fiber in 1 layer, or you can do as much as fill the entire part. We usually advise for something in between, and we have a few strategies that we can discuss. Can we please explain how to fasten the concealed nut in the last example? Sure. So what you don't see in this concealed nut is a bolt that comes up from the underside. If you can see where my mouse is, a bolt that comes up from the underside of that top plate and comes through. So if you look above the nut here, you can see there's a little bit of a screw coming up through, and so that's how it's actually fastened. How does your fiber material handle the high temperatures of a nearby welder working on a clamp part? So depending on how close you are, it handles it differently. We have all kinds of stuff on the material data sheet for how temperature resistant. Generally, the Onyx and the fiber starts to deform at like 140 degrees Celsius, but I'm not 100% sure on that exact number, and it varies fiber to fiber. Generally, if you're at the distance we just showed and you're just tacking the part, you'll be totally fine. If you want to weld the entire part, your fixture might be sacrificed in the long run, but it will not be sacrificed before the weld is successful. We've had plenty of people use our parts for welding fixtures before, and really it depends on a few factors, mostly how far your fixture is from the actual weld. Those pinholes for locating purpose, do we print them out or CNC machine afterwards? You can bore out Onyx parts if you want. We don't explicitly recommend it, but you can if you want. Generally, we just print them out. With fixturing, the tolerances required are generally less than you'll see from like a production part. So the tolerances that we can hit on our fixturing apparatus is plenty accurate, so that we can just print them. The other thing to note is that while our parts are really strong, their surface hardness is not dissimilar to what you would expect from like a medium to hard plastic. So a press fit is a little more malleable than what you would expect. How is the fiber oriented? Well, that's it really depends. So fiber is oriented on the same plane that you would be printing a part. So if you can look at this example on the side that we're currently on, in that case, what that means is that the fiber is oriented basically flat. Where you can see on the top right corner, there's some loops. In terms of layer-to-layer orientation, we have a few different fiber regimes. One is called isotropic fill, which is what this fiber is, where it does basically zigzags across the entire layer of the part. And the other one is called concentric, where you just kind of loop in from the outside of the part or loop out from an inside hole. But that's kind of the base granularity. Again, we have a lot of resources on our website, and I would encourage you to explore some of the guides we have on how to allocate fiber. How does the wait? 1 second. Oh, okay. So some couple people asked about inserting nuts into parts. So there's a couple ways you can do it. The way that we discussed here is just to capture the nut. So you print the entire part, and then you just put the nut in afterwards because that cavity is there. You can also insert nuts during the printing of parts. So because our print bed is can be taken out and reinserted with a repeatability of about 10 microns, it means that you can pause a print midway, you can insert a nut, and then you can restart the print, and the nut will be fully captured. There's a couple things that are less than optimal about this. One of them is that you're generally that means you're putting the nut on a z-axis on like not a fissure, but on in between layers on a z-axis. You're kind of pulling against the z-axis. So that's not generally great. There's a couple other strategies where you can put the nut in sideways and then print over it, and that's awesome. But in this case, we didn't really need the nut to be embedded in the part as much as just like pressed in and then screwed afterwards. So what's the best comparison between this and, say, a metal material strength-wise? So it really depends on the fiber. It depends on the type and amount of fiber you put in. But if you fill a part with carbon fiber, the part will be stronger than aluminum in flexural strength, and I think it's about as strong as aluminum in most strength tests you'd see. The one exception is obviously in z-axis because we're laying the parts like you'd lay a normal composite in one plane. Say I want to print a dovetail joint. How do I most efficiently work with fit and tolerances? So printing printing super precise joinery is not an art form as much as kind of something that's learned, an intuition that's learned. As we say that our prints aren't exactly precise, and so it's really easy to print parts that don't fit the first time. The thing that we generally advise people to do when they're working with joinery like that is to print a unit test. And so what we mean by a unit test is if I want to print a large part that has a dovetail joint, I'll take a small subset of the male and female parts of that dovetail and print them and check the fit there. And if that fits well, then I'll scale that up and print the large one. And if it doesn't fit well, then I'll maybe adjust the dimensions on the small one and print it again until it does fit well. And then once it does, then I'll print it on the large one, the larger assembly, and it'll work well by itself. So the reason that that's good is, again, because our printers are very repeatable. But as you kind of print more and more, you can develop a bit of an intuition on what tolerances are best. It really depends. I couldn't give you a specific number because it really depends on what you're printing and how large of the dovetail you're printing and what the specific geometry of it is. But it's something that is definitely doable. Do you have experience with threaded metal inserts, i.e. tapping inserts and heat set inserts? In fact, we have a whole webinar about them. We do talk about them pretty often. The one thing that makes them inferior is that they're a little easier to pull out than, like, say, a captured nut like this. In order to pull out a captured nut like this, you'd have to basically just destroy this part because the fiber is physically impeding the nut from being pulled out. With a threaded insert or heat set insert, you just kind of have to pull the insert out. We do use them. They're super useful in like a lower load screwing or bolting application. They're definitely something you can use readily. And as we said, there's a whole webinar on them which you can access through our website, and there's several blog posts about how to design for them and what's the best practice. Lots of questions, of course. Do you have plastic welding experience with onyx, chopped fiber, and fiber filament? So we're interested in making large parts. So we do not have experience with plastic welding. We do have experience making large parts. Generally, we don't try to alter the parts too much from a thermal perspective after we print them. And I dare say that if you do, it might sacrifice the strength of the fiber. But it's certainly something you can try. The way that we make large parts is we CAD joinery together, and then we glue that joinery. So we have a couple of customers that do this very well, where they're making enormous printed parts by CADing parts that fit together, kind of like puzzle pieces, for lack of a better word, and then gluing them. And because our glue strength is really strong, and because they're CADing it in a way such that for the part to separate, it will have to geometrically alter the fiber, and then you're leveraging the fiber strength in the joint as well. We've had some success with printing larger parts. Is delamination an important issue for these parts under high loads? Delamination is kind of always an important issue when it comes to FFF printing. But when you bolt these parts together, the odds that something's going to delaminate and the risks associated with delamination are not mitigated, but they're greatly reduced. And so that's kind of the reason we talk about bolting through these parts for extra strength. Sorry, Alex is answering the question really quick. So how are the fibers oriented? Will there be support for partial fiber reinforcing as opposed to a full layer? The answer to that question is probably not for a while. The fiber algorithm we work on constantly, but that's probably not something we're going to get to right away. There are ways you can get parts to be reinforced in specific areas. We launched a new tool recently called Inner Holes. It's for concentric, and it will start from the inner hole of a part and reinforce out from there. There are ways to geometrically leverage that to get specific reinforcement. Essentially, you just put a small hole in a specific area of the part, and you call inner holes, and it'll reinforce that area as opposed to the whole part. But generally, we don't have like a specific, whether it be a specific feature area request, whether it be like selective supports or selective fiber. Those are not things that we have right now. Overuse cycles within 3D printed fixtures wear down quickly and reduce repeatable precision. Depends on how intense the use case is and how intense and how abrasive the part you're working with. For a CMM fixture like this, or for a welding fixture, probably not. For a gripper jaw, depending on what it's gripping, we have gripper jaws out in the field that work for thousands and thousands of duty cycles just fine because onyx is pretty inherently tough, and the parts behind them are very stiff. But if you're using something in a particularly abrasive environment where the fixture itself is being abraded, then yes, it would wear down and it would probably affect the precision. We've had some slight issues with that in the past, but there's some pretty easy workarounds for it. And yeah. Can we talk more about joining chopped fiber carbon filament parts using adhesive? Sure. From a usability perspective, it's very simple. We use Loctite 401, which is a cyanoacrylate, not similar to like what you would expect from like a normal super glue. We apply it over the surface, and we just kind of join them. A couple of important things are making sure that you're using a type of joinery, so don't just like stick two flat surfaces together, glue them, and expect them to be full strength. Use some strategy where in order to like the parts fit together in some way, and the glue is just securing the last axis. As we said, two methods of holding a part together. And make sure that when you have that joinery, that all the surfaces are touching each other. So if your tolerances are off on something like that, there's probably a gap between one or more of the surfaces that are supposed to be touching, and then that whatever glue you use won't be effective in that area. So you want to make sure that your parts are fitting together snugly before you think about gluing them. And then once you glue them, they'll be pretty strong parts. We have a case study coming out in hopefully the near future that will discuss the utility of this and kind of how you do it. We have a couple of example parts about it, but if you have more questions, feel free to shoot us an email and we can talk more in detail about a particular use case. What's the general tolerance of a dovetail joint from male to female? We kind of discussed this before. Part tolerance is around 5,000, so you can expect something like that. But again, it's very repeatable, so what we say is, again, to print unit tests, verify that your dovetail will work on a small scale and then print it on a larger scale. One important note about unit tests is making sure that you're printing the parts in the same orientation that you're going to print the small parts in the same orientation you're going to print the larger parts. So a good example of this is like if you're printing that, like the example we did in our presentation, if you're printing the female part of that dovetail flat such that the dovetail is kind of an overhang, and the male part flat such that the shape of the dovetail is flat on the build plate, make sure that you're printing the unit test in the same way. Don't flip that female part up, because then it will not be an accurate representation. How strong are printed threads? Depends. You can screw into them generally, but they're not ideal. We like bolting through things. We like using captured nuts. We like heat set inserts more, but it's distinctly possible, and it does work. It's always a mixed bag. And again, a threaded joint like that, especially if you're screwing it in, unscrewing and screwing a lot, will machine itself down to be a lot less useful in time. Is Loctite 401 able to glue metal and plastic together? I honestly don't know the answer to that question, but we could look that up. Let's see. Is onyx electrically conductive? No, because the plastic itself is not. The fibers inside might be, but generally it's resistive. Let's see. Sorry, there's a lot of questions. We're trying to sort through them and find ones that are best to answer for everyone. What's the life cycle? What's the life cycle for extruded part before it begins to degrade due to moisture absorption? We haven't done a whole ton of research on this. but we can tell you that parts have worked in the field for like months and months and not had any issue. If you're using something in a high load part, maybe it would degrade over time, but that's not an issue we've really ever run into. How does Onyx hold up to coolant from a CNC machine? Onyx is generally moderately resistive to chemically abrasive, chemicals that will like destroy most plastics. It's pretty good about that since it's nylon based. So I would say just as a kind of a rule of thumb, if nylon, if you're like standard nylon 6 or nylon blend like that would stand up to your machine coolant depending on what you're using, the printed parts definitely will. We definitely have people who are using these in CNC machining centers and not having any issues. Let's see. So can you discuss the software and how it defines the layering of the fiber? So this webinar is a little more high level than fiber. We have some really good webinars that talk about at a more granular level how you do lay fiber. But for now, for this webinar, we didn't. I would recommend that you look at those webinars for a more detailed thing. I can give you a super quick explanation. Basically, on each layer of fiber, you can designate a group of layers or a single layer, and you can define basically what fiber laying regime you want to use, whether it be the concentric I explained before or the isotropic. Also, Alex just reminded me. In the last month, we recently just launched an online demo of Uyghur. So basically, our cloud software, you can now use if you just put your contact information in. You don't need to request a demo or anything fancy. You just go to Uyghur.io. You register as a new user. You won't be able to obviously print because you don't have a printer, but you can try slicing and laying out fiber by yourself and get to know the software a little bit. It's a really cool, intuitive software. So I'd recommend that all of you check it out. Can you repeat the orientation while printing fixtures? You can. It does kind of, you could print all of your multi-part fixtures in the same orientation, but then the question becomes, why are you not printing them as one part? So generally, you don't want to print your fixtures in the same orientation, but they're certainly one of the biggest reasons you could is print time. So if you have basically a large base plate and a couple posts, you could print the base plate and the post separately, and then you would circumvent the need for a lot of support material. The thing you'd then have to understand is your parts would not be as strong, probably. What's the strongest form of joinery for 3D printing? Honestly, bolting parts together with like a lap joiner or any good mechanical with a pin or any good mechanical constraint like that. There's a few things that beat bolts from a strength perspective. Let's see. Does Markforged print parts on a contract basis? No, but a bunch of the 3D printing resellers, 3D printing services like Shapeways and 3D Hubs do. So if you want to try out some of our parts like that, definitely look at their websites. But please talk about editing supports prior to printing. So there's not too many things you can do to edit supports. We just launched a new feature called Turbo Supports, which makes printing supports a lot faster and a lot more accurate, which is really nice. As I mentioned before, we don't have selective supports and we don't have soluble supports. The only other thing you can really change is the orientation of the supports. So you can orient to the default direction of the zigzags that the supports print in whatever way you see fit. This is actually relatively important for a variety of different unique geometries. There are ways that are better to support than other ways, and we discussed some of those in some of our earlier blog posts and guides like that. Let's see. To remove the glue, what's the method? So the reason we didn't really discuss glue in this area or in this presentation was because Loctite 401 is not really removable. So once you glue two parts together, you're not going to get them apart, or you really shouldn't expect to without sacrificing the strength of the part. So that's why we kind of we like using mechanical connections better for these multi-part tooling assemblies. Let's see. Are there any, on what surface do the fixtures form? Are there any clearance between the assembly parts? In this case, because we're bolting them together, no, but you could have clearance between the parts if you needed to. The bolt holes on the captured nut do have a little bit of clearance because we don't want them constraining the part, we want the pins constraining the part in the XY. Let's see. Let's see, sorry, just looking through a couple more questions. When bolting with a cap screw, is a washer recommended, or can the bolt head be seated directly into onyx and then torque tighten without detriment to the onyx? If no washer, how robust is the surface of the onyx to the bolt tightening? Generally, I advise everyone to use a washer and a lock washer when you're doing anything, whether it be metal or plastic. You can, so like if you look at some of the examples that we have here, these do not have washers. They're just socket head cap screws that are bolted right into the surface, and that's because it's a lower load application. If you're really torquing down a screw, what's going to happen is the onyx is kind of curl downward with that bolt, because onyx itself is not very hard. So on a micro level, the parts are not very strong. On a macro level, the parts are super strong. So adding a washer kind of transitions from that micro level of like small deformation or like surface hardness to leveraging the full strength of the fiber. So it is generally better practice. Something about surface smoothness. So what level of surface smoothness can be achieved off the printer? So any of the parts you see here that are all over this presentation, none of them have been post-processed in any way for a surface finish perspective. Our surface finishes with onyx is really unreal, and if you can look at it on these close-ups, it's virtually impossible to see the layer lines in the part, and they're super precise. They're not like perfectly smooth, but they are very very good surface finish. You're not going to see a lot of weird deformations on onyx. When would screws be acceptable in mating printed parts? I'm not sure if you're trying to screw into a part. You can. I mean, just like kind of what you'd expect with a wood screw. Like you don't really, if you're using a wood screw, you don't really expect the part to come out. If you're screwing into an Markforged part, you don't really expect the screw to come out. So it's useful. If you're trying to do something really quick and dirty and it's less precise, I would say that's an application you could use. I wouldn't generally not recommend it overall. Awesome. So it looks like we've kind of so last person is, where do we find pricing information in these printers? If you've registered for this webinar, we will be reaching out to you at some point. You can also request a quote on our website. You can also try to contact your local reseller, which is another thing you can do, and they can get more detailed pricing information. With that, thank you very much for attending this webinar. This is the largest webinar we've ever done, and I hope we taught you some interesting stuff and answered your questions as best we could. Yeah, thanks everybody. Have a good day.